Alright, hell yeah. So we're going to do a little proof. This is dynamics, and this is some tough stuff. Hell yeah. And so we got SpongeBob today, and what we're going to go over is relative motion of 2 points on a rigid body. And so the definition of a rigid body is that if I have 3 points on a rigid body, these points always stay the same distance apart. I can move this rigid body around, I can even rotate it, and those same 3 points stay in the same position. We're going to use a pen today, and this is going to be point A, and this is going to be point B. If I move this pen around, the distance between point A and B have to be the same. And so just keep that in mind, because that's going to be useful for what we can have and what we can't have. And that really simplifies, you know what I mean, the motion that we're going to be able to see. So here's the definition of relative motion between points A and B. They're going to yield the following relationship. We're just going to look at the velocity one. The velocity of point B over here, we're just interested in that one, is going to be the velocity maybe that we know. I know what point A is doing. And then also it's going to be the velocity of point B as seen from point A. So that's where we're going to bring SpongeBob in. Cool. And this is where I kind of got confused, because if I put SpongeBob on point A and fix him to point A, just pretend like SpongeBob and this pen are the only thing in the universe, and what we have is this motion right here, and it's just constant velocity. SpongeBob doesn't even know he's moving, and it looks like that point is stationary. So I think this is a very good demonstration to do, because this is what I got into my head, and it's completely wrong. So let's read on, because it shows. This is the only sentence in this whole textbook that explains that if you're going to do that, if you're going to read this as the velocity, this is velocity of A, this is the velocity of B, and if I say the velocity of B as seen from A, if I'm going to use that, this is the relative velocity, velocity of B as seen from A. Well, it seems like, hey, I could put myself at A. Cool, SpongeBob and you are at A, but you have to have yourself non-rotating. If you're non-rotating, now you will see a difference. SpongeBob is looking straight that way. Whoa, out of the corner of SpongeBob's eye, he can see that this thing is going from there to there. And so let's read this definition. It says, it is useful. Let's read this subscript. So this subscript denotes the motion of B as seen from A, or relative to A. It doesn't even see as seen, that's just something that we can say. It's like, hey, it's as seen. But if you are going to use that term, as seen from A, let's read on. It is useful to recall that the velocity of B as seen from A, it's same for acceleration, but can be viewed as the velocity of B as seen by a non-rotating observer attached to point A. So there it is. Seen by a non-rotating observer attached to point A. And so we're going to view the velocity of B. So if I put SpongeBob at A, we have to have SpongeBob not rotate. And then B can move. We do see some velocity, and that's what we're going to see. Okay, and then the whole take-home of this is the only movement that SpongeBob can see is tangential movement. And so I'm just going to do this tangential movement just a little bit. But if SpongeBob is at A and is fixed, this point B can spin all the way around SpongeBob. Hell yeah. And SpongeBob is going to notice that and calculate that. And be like, yeah, that thing is moving and I can calculate that velocity. And SpongeBob is just going to calculate the tangential velocity. That's what SpongeBob wants to know. Booyah. But SpongeBob was able to see that because he attached himself to point A, but then chose to be like on a gimbal and not rotate. But that's the take-home part of that. Okay, we're going to get into the proof on the next page. And what this says is that, you know what I mean, here is point A, here is point B, and we're going to have both point A and B moving in the same direction. I'm going to show that in a second. And then also point A rotating, point B rotating about point A, because that's what SpongeBob saw. And then this just shows like, hey, we can either do it as a vector, or we're going to have this plus this as a scalar. Hell yeah. So let's go through the scenarios that we can have. Again, this is point A, this is point B. The simplest thing we can do to this pen is have point A just move this way in a line, maybe 1 meter per second. So that's all we're going to do, is just move it like that. Obviously, it's not moving 1 meter per second, but you get it. We have some sort of velocity. And what happens, if this is point A, this is point B, B has to follow. So I can say the velocity of this point B is the same as the velocity of A. Cool. Now, is that the only thing we can do? Well, let's step back. What are the things that we can't do? We define this as a rigid body. Again, a rigid body is where you have points on a rigid body. These are particles or chunks of mass. And what we're going to say is that this thing doesn't stretch out, it doesn't compress, it doesn't warp in shape. So hell yeah. So if point A moves there, and it's going to be in this linear line, point A has to follow. What point A cannot do, and I'm just going to say, let's say point B, I'm switching the points around because I did this video like opposite. This is point A, this is point B. If point A is stationary, what point B cannot do is move towards point A. It can't crunch in. What point B cannot do is move that direction. It can't stretch out this pen. Now, is there other directions that point B cannot move? Yeah, point B can't move over there. The pen would stretch out. If point A is stationary, this point cannot move that way. It cannot move that way because the pen would crunch in. That leaves the only direction this can move is up and down if this pen is horizontal. So it can move up and down, just a little bit. And then the second it does move up and down, it can't move up anymore, because if it moves up anymore, the pen's going to stretch out. So the only direction it can move is tangential. And if point A is stationary, what we can see is the only motion, and if this velocity is constant, the only motion, we just get a relationship that we're constantly changing the angle of this pen. So the motion, we can definitely calculate this velocity. I mean, it's a normal velocity, tangential velocity. It's a normal number, on that velocity. Hell yeah. Alright, so, we got 2 minutes, and I don't want to do this again. Booyah. So point A and B can move like this. Point A and B can also move like this. That's chill. And you can be at an angle, and point A and B can move like this. But I'm going to show that point A and B can move like this. So point A is moving just chill, but then point B is going hella faster. But again, if I put SpongeBob on this pen, SpongeBob doesn't know SpongeBob is moving. So all SpongeBob is going to see is this pen do that. And SpongeBob is going to calculate that. Hell yeah. And so the velocity of this is going to be whatever point A was moving. That's going to be the, velocity of the tip of this pen, velocity of B, is going to be the velocity of A plus the relative motion. And that relative motion can only be, tangential motion. And tangential motion is, how to calculate that? Well, we quantify that as this angle is changing at a constant rate, and the distance to that point, that's angular speed, times the distance, is that tangential velocity. So that's what we have, is that this relative velocity of SpongeBob's, what he's witnessing, is omega cross r as vectors, or scalar component is just omega times that radius. But that is, and this quantity is a tangential velocity. So that's what we have. We have 18 seconds. I think that's what I want to do for this video. So hell yeah. Thanks for joining me. And hell yeah, that's a video.